All right, let's dive in. Today, we're going under the hood of Ethereum to really understand the engine that makes it all run. The Ethereum Virtual Machine, or EVM for short. If you've ever wondered how smart contracts actually work, how they execute on the blockchain, well, you are in exactly the right place. And this quote really just nails it. It gets to the very heart of what makes Ethereum so different. It's not just a system for digital money, it's a global platform for computation. It was built from the ground up to run code, and that simple fact is what makes it so revolutionary. So here's how we're going to break this all down. We'll start with the huge idea of the world computer. Then we'll properly meet the EVM itself. We'll look at its main building blocks, accounts and contracts, and then talk about the gas that fuels the whole system. After that, we'll take a peek at how it actually executes code, and we'll wrap up with why any of this really matters. Okay, so let's kick things off with this massive, almost sci-fi concept, this idea of Ethereum as a single, shared global computer. I mean, just think about that for a second. A computer that no single company, no government, no person owns or controls. Anyone on the planet can use it to run applications. And because it's decentralized, there's no off switch, there's no single point of failure. Now, to make a wild idea like that actually work, you're going to need a very, very special kind of operating system. And that special operating system, the absolute core of this world computer, is the Ethereum Virtual Machine. Put simply, the EVM is the environment where every Ethereum account and every single smart contract lives. So when you send a transaction or interact with a decentralized app, what you're really doing is telling the EVM to wake up and execute some code according to a very specific set of rules. Okay, so this brings us to a really important design feature. You'll hear the term Turing complete, which is a fancy way of saying a machine can solve pretty much any computational problem you throw at it. The EVM is designed to be almost that powerful. We call it quasi-Turing complete, but it has this crucial limitation built right in. It's like a safety switch, and that switch is what stops the whole thing from grinding to a halt. We're going to find out that switch is called gas. So how does this virtual machine actually get any work done? Well, if the entire world is basically populated by two kinds of things, accounts and the smart contracts they talk to. Right, so on one side, you have externally owned accounts, or EOAs. That's probably what you have. It's your wallet, the one you control with a private key. You can think of these as the users of the system. Then on the other side, you have contract accounts. These are different. They don't have private keys. They live on the blockchain and are controlled entirely by their own code. They're like the programs, or maybe like autonomous robots just following their instructions. And these programs, these smart contracts, are unbelievably versatile. They can do all sorts of things. A contract can act like a simple public database. It can enforce complex rules, like a multi-sig wallet that needs 3 out of 5 people to approve a transaction. It can manage an ongoing relationship, like an automated system that pays out a bounty to whoever fixes a bug first. Or it can even act as a software library, providing tools for other contracts to use. And that brings us to maybe the most critical piece of this whole puzzle. If you have a global computer that anyone, anywhere can run code on, how on earth do you stop people from abusing it? This is where gas comes in. I mean, that's the million-dollar question, right? What's to stop me from writing a malicious program with an infinite loop and just deploying it to clog up the entire network forever? The answer is both incredibly simple and totally elegant. You have to pay for every single step of computation. And that fee is called gas. Every single instruction, every calculation, every time you store a piece of data, it all has a tiny cost associated with it. This is what prevents spam and denial of service attacks, because trying to run a really complex, messy program, or worse, an infinite loop, would become ridiculously expensive, really, really fast. So when you send a transaction, you actually set 2 values. First is the gas price. This is how much you're willing to pay for each little unit of gas, kind of like the price per gallon for your car. Then there's the start gas, which is now usually called the gas limit. That's the maximum amount of gas you're willing to buy for this whole transaction. It's like saying, I'll pay this much per gallon, but I'm not buying more than 10 gallons for this trip. If your code runs out of gas before it's done, the transaction fails, but you still pay for the work the network already did. All right, now for the really fascinating part. Let's pop the hood and take a simplified look at how the EVM actually thinks, how it processes the instructions we give it. The EVM uses a concept called a stack. The easiest way to picture this is to imagine a stack of plates. You can only put a new plate on the very top, and you can only take a plate off from the very top. You can't just grab one from the middle. This last-in, first-out structure is exactly how the EVM manages data and instructions. So let's trace how this really works. We're going to watch the EVM solve the simplest problem imaginable, 1 plus 1. The raw code the EVM reads is called bytecode. It looks like this jumble of numbers and letters right here. Now don't worry, it looks intimidating, but we're going to break down exactly what it's telling the EVM to do step by step. Okay, first up, the EVM reads the first part of the code, 6001. This instruction is called push 1, and it just means push 1 byte of data onto the stack. The data it's pushing is 01, which is just the number 1. So our stack, which was empty, now has one item on it, the number 1. Next, the EVM reads the next chunk of code, and what do you know? It's exactly the same, 6001. So it does the same thing again. It runs the push 1 instruction and pushes another number 1 onto the top of the stack. So now our stack has 2 items, with the newest one on top. And for the final step, the EVM reads the last instruction, 01. This is the opcode for add. The add command tells the EVM to pop the top 2 items off the stack, add them together, and then push the result back onto the stack. So it grabs the 2 ones, adds them to get 2, and puts the result, 02, back on the now empty stack. And just like that, the EVM has solved 1 plus 1. Now push 1 and add are just 2 examples. The EVM has a whole dictionary of these simple commands, called opcodes. As you can see, there's a unique instruction for every basic action, from multiplication to checking the current block's timestamp. Every single smart contract, no matter how complex, gets compiled down into this fundamental machine language. So, we've gone from this huge, futuristic vision of a world computer all the way down to the nitty-gritty details of opcodes and stacks. But why? Why go through all this trouble? Well, the entire design boils down to creating a truly secure and trustless system. Everything about the EVM is built for security in an environment where you can't trust anyone. We've talked about gas. It makes attacks economically impossible. Then there's sandboxing, which means every contract runs in its own isolated environment. It can't just reach out and mess with another contract's code or storage. And crucially, execution is deterministic. That means if 1,000 different computers around the world run the same transaction, they are all guaranteed to get the exact same result. That right there is the foundation of blockchain consensus. So, what's the big takeaway here? The EVM provides this incredibly secure, predictable, and decentralized environment for running applications that can't be stopped. The foundation for a trustless world computer isn't science fiction anymore. It's here. The only question left is, what are we going to build with it?